what we were doing till now? Do you all remember what we have done till now?
Sir, microcanonical.
Yeah, different kind of ensembles in short. So first one was here microcanonical. So what was the properties of this microcanonical ensemble? It was an isolated system. Do you all remember?
Yes, sir.
What does ensemble means basically? What does ensemble means? A huge collection of what? Identical systems. Clear? Now let's say you have one system. You have another system. You have another system. You have another system. Now this, all of the systems are identical and they are what? Isolated from each other. Can you see? Think of this, whatever is sitting in between them is what? Your insulator or something. So over here, what are constant for in each ensemble? Number of particles, volume, and energy. Do you all remember?
Yes, sir.
And it was isolated system. And second was one here, canonical. So what's the difference between this and this? In canonical ensemble, think of this as this one. All of these ensembles are in contact with each other. Clear? In this manner. If they are contact in each other, then what? The energy is allowed to be exchanged between each ensembles. Is it clear?
Yes,
This
sir.
was completely isolated. These are in contact with each other. These are in thermal contact usually. This is usually what we want. This is usually this kind of ensemble which we will be using. So over here, what? Energy is being able to be exchanged. Energy is being exchanged. But what is remaining constant? Your temperature is remaining constant. Clear? So that's why we write in terms of NV and T. Clear? Exchange of energy is allowed. Basically, it was here closed system. And third one was here what? What was your third one? Grand canonical. In your grand canonical ensemble, what was the property for this one, this kind of ensemble? You had a system and let's say you have this kind of such small boxes, but they are, let's say, kind of dashed. So what will happen is the number of particles are also allowed to be exchanged between each boxes. Clear? From here to here, number of particles can also move, energy also can get exchanged because they are in thermal contact. So these ensembles are what? Defined by not N but mu, V, and T. So this is basically an open system. Is it clear now? Is it clear?
Sir.
Okay. So today we are going to do with what? Boltzmann Canonical Distribution Law. Boltzmann Canonical Distribution Law. Now let's consider, again we will consider the same thing what we were doing previously. We have a box and they are converted into small cells. Clear? But over here, they comprises of n number of ensembles. And now let's consider a small cell. These are your small cells. Do you all remember the small cells? N1 particles will have energy E1, so on and so forth. So your total number of particles is what? N1 plus N2 plus N3 plus so on and so forth. Is basically what? Your constant. Clear? Is this point clear?
Yes, sir.
Now the second thing is what? The number of particles is fixed, so if we disturb, then the variation in delta n will be how much? 0. Is this point clear? Is this point clear? If you differentiate this constant, then it's not clear, no?
Sir.
Yeah? Yes? Is it clear? Yes, sir, someone has written.
No, sir.
Okay, this point is not clear. One thing is, if you differentiate any constant with any variable, how much you'll get? How much you'll get?
0, sir.
0, exactly. So that's why fluctuation in delta is 0. We are just taking a differentiation of n, which is basically a 0. Is it clear now?
Yes, sir.
Is it clear or not?
Yes, sir.
Now the second thing is what? Or what you can write? Or delta n is equals to n1 plus delta n2 plus delta n3 plus so on and so forth is equals to 0. Is this point clear? Because this is constant, so any difference, or if you take a derivative of n with respect to any variable, how much you'll get? You'll get 0. Fine.
Yes, sir.
Now the second point is what? Your total energy is constant. We are considering a canonical ensemble, and we are considering the energy to be constant. Is this point clear or not? Is there something wrong with this?
Clear, sir.
No. What was the definition for this canonical ensemble? The definition for the canonical was what? Your energy was allowed to be exchanged. But here we are considering the total energy of a system is constant. Is this point clear or not? Why we are considering this to be constant? But we are using the canonical distribution. Do you see? Is there some problem? Is there some problem over here? I'm asking to everyone. So what were what of the which quantities were fixed in your canonical distribution? Can you tell me? Just now we did. Particle, volume, and energy.
Sir, energy exchange.
Okay. In canonical, energy was allowed to be exchanged. But here we are considering the energy to be constant. Why? Because it's not this one, but the energy of the each. If you consider each cell will have energy E1, E2, E3. Ensemble will have this energy, And if you consider the total energy of this whole ensemble, then that will be fixed. That will be constant. Is it clear?
Yes, sir.
Even is being able to exchange between different systems, but the whole energy is constant. Clear? So that's why we can take the total energy of system as constant. Now what does this means? Yeah, energy E is given by what? E1 into N1, if you all remember, E2 into N2 plus so on and so forth, which is here constant. Now again, if you take a derivative of this E, then how much you get? You'll get 0. Is that fine? Let's
Yes, sir.
put it in this manner. Let's say you took, because E is constant, you take a variation with respect to N. Let's say this is 0. Then we can we write dE equal to 0? This cross multiply it over there. And can we just write delta E equal to 0? So we are doing exactly the same thing over here. Yeah. This delta you can take it as D itself. Is it fine?
Yes, sir.
Now the third point is, for the thermodynamic equilibrium, what is your maximum? For thermodynamic equilibrium, or basically in equilibrium, what your W should be, omega should be maximum. Clear? Or we can just write, do you all remember, because we have discussed this explicitly, why for thermodynamic equilibrium your total number of microstate or thermodynamic this probability should be maximum? We have discussed it previously. Do you all remember?
Yes, sir.
So that's why, or basically log of omega we can write. This is also should be maximum. We are multiplying both sides by log. And the variation of this log of W should be how much? Log of omega should be 0. Because this is maximum. So this was a condition for your thermodynamic equilibrium, which we have done it in the previous lecture. You just check that lecture. From that we got this beta also. Now everything is here. Now we have to know what is the distribution or total number of microstate omega is given by how much? For cells with equal size is given by n1 factorial, n2 factorial, n3 factorial, so on and so forth. Do you all remember this? Indira,
Yes, sir.
do you remember this? When did we introduce this? When the cells were of different sizes. Do you remember? And from there we say that for the cell with equal size will be given by this one. This was a probability of particle N1 being in a box with energy E1, N2 in energy E2. Do you all remember? If you all remember. You just revise this because this is very important. So log of omega will be given by what? Taking log on both sides, log of n factorial divided by n1 factorial, n2 factorial, n3 factorial, so on and so forth. So for log, what we can do? By using the property, we can just write this minus log of n1 factorial, n2 factorial, n3 factorial. If you have any problem, just let me know. Is this step okay? N factorial, what we can write this as negative with log of n1 factorial plus log of n2 factorial plus so on and so forth. Where we have used the property, do you all remember log of a by b should be equal to log of a minus b, and log of a into b is given by log of a plus log of b. Here we have used this property. Now we'll use what? Stalling approximation. Do you all remember stalling approximation, which was given by, what was the stalling approximation? For log of n factorial can be written as n log of n minus n. This is your stalling approximation. So we will put this over there and it will be what? N log of n minus n. Over here, let's put it in terms of summation so it will be easier. Is this okay if I write this in this form? Here I have not used the stalling approximation. I'm just writing this whole term in terms of summation. So it will be easier now. So log of omega can be written as n log of n minus n, and again we'll use the stalling approximation to get what? Summation over I, ni log of ni minus ni. Now what we'll use? We will consider the condition when the system is in thermodynamic equilibrium. System is in thermodynamic, let's write thermodynamic equilibrium. As we have already seen, for thermodynamic equilibrium, what? This delta of this should be 0. If we differentiate both sides, what you will get? Delta log of omega should be equal to, this is just a constant. If you take a derivative of this, how much you will get? How much you will get? Should I do it in terms of differentiation or should I do it in terms of delta? This is basically 0 minus 0. This is also 0 minus summation of I. You have to take a differentiation or derivative of this whole thing which is sitting over here. Now next, what do you do is, at thermodynamic equilibrium, this thing should be how much? 0. So we put this 0 over here, summation of I. If you take a differentiation with respect to this product rule we are using, delta, or what you can do is, first let's put it in this manner. Log of delta ni differentiation of log of ni plus log of ni delta of ni. We have used a product rule over here, minus delta of ni. I'll just elaborate this step one more over here. Just you can think of this as a variation with respect to n, let's say. N is just a quantity which this whole thing depends on. Delta of ni log of ni. This we are finding. This what we can do is delta by delta n, let's write. With respect to anything it could be actually. So it will be ni log of ni. So what we can do, product rule, we can take ni outside and take a product of this del by del n of log of ni. Clear? Plus log of ni d by dn of ni. Is it clear? Now, if you take a derivative of this with respect to log ni, how much you will get? 1 by ni, or let's do it even in a simpler manner. Let's write this as del of ni log of Ni delta of Ni. This two will cancel out by, let's put it in this manner, d of Ni by d of n. Let's put it in this manner. Plus you already have log of Ni dNi by d of n. So how much you will get? Derivative of log of Ni is basically Ni, and this, what we can write this whole thing del n by del Ni, what we are basically writing, this n will just cancel out, will be common from everything. So this will just write as, for timing, let's write the whole thing, plus log of Ni d of Ni by d of n. This is here one of the quantity. This two will cancel out. And finally, you'll end up with what? D of Ni by D of n plus log of Ni D of Ni by D of n. Now this we just substitute over here. Now over here we have, this is basically what? Delta of Ni we can write as D of Ni by D of n. But basically what we can do is we can write this quantity of, basically n will come out as common and it will be just delta Ni. We are taking a differentiation with respect to n. Let's say n is some variable. This will basically how much? This summation of over what? Ni. This is how much you got this one? This whole quantity, how much we got? D of Ni by D of n plus
log Ni
log Ni
d by dn and I.
Ni, and basically minus, this is dNi by dn, because we are taking the derivative on the both side. Okay, in this step what we can do is we can take del by del n of log of omega is equals to the derivative of this whole thing. Clear? Here is a constant n log of n. This is a constant, so this will be 0. This is n, this is also will be 0. And remaining quantity we have at the end dNi by dn. Exactly the same term. Is it clear? Okay, so after that what we can do? We can take dn common, because dn doesn't depend on anything. Summation of I in I, and you can take dn on the other side. This let's just write as delta or d. Anyway, let's write it as dni plus log of ni d of ni minus d of ni, and whole thing was divided by d of n. Do you all see? Take a derivative with respect to n, so that we can remove and take it on the other side. 1 by dn. This we take it on the other side, and basically you'll end up with what? Summation of I, Ni, and just writing in terms of delta, log of Ni, d of Ni minus delta of Ni. Sorry, this Ni will cancel out. There you go. We don't have this Ni, because from here it's basically delta Ni. Ni delta Ni. Clear? And if you see, this two will cancel out, and finally we are left with what? At thermodynamic equilibrium we have log of Ni delta Ni. Is it clear? And this should be 0. Now basically what we are finding Ni. Now how to find Ni from over here? And apart from this, we have two more conditions. Or basically what we can write each condition. This is here condition 1, I, log of Ni, delta Ni should be 0. This is your first condition. And second condition, if you remember, all Ni, sum of all Ni should be N1 plus N2 plus N3 delta of N3, which we can write as what? Summation over I, delta of Ni should be 0 from previously. And third one was what? Delta of E, if you all remember. Delta E energy, which is given by what? Have we written that one? Yeah, delta of E should be 0. Delta of E should be 0, which is basically what? Delta of E1 delta of N1 plus E2 delta of N2 plus so on and so forth should be 0, or simply summation of EI delta Ni should be 0. Now, if you check, there are three conditions which has to be satisfied simultaneously. Yeah. And for this kind of condition to be satisfied, what we can do is we can multiply it with certain constant and add all this three quantity. Yeah. Because this three quantity has to be satisfied simultaneously, what we will do is we will this consider as 1, this as 2, and this as 3. We multiply 1 by what? Let's say some constant lambda 1, this by lambda 2, and this by lambda 3, and add all this 3. Yeah, that is why how the simultaneously it will be 0. That condition will be satisfied. So this is how do you do. I think the same thing which you have done in your Lagrangian undetermined multiplier. Do you all remember that in classical mechanics? For the time being, the condition is basically this 3 should be satisfied simultaneously. And in addition to this, you have this delta Ni sitting over here, 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 everywhere. So for all this quantity to satisfy simultaneously, what do we usually do? We multiply this with certain constant and add them up. From there, we will get a condition when they will be satisfied simultaneously. So the first quantity will be how much? Lambda 1 summation over I log of Ni delta of Ni plus lambda 2 summation over I delta of Ni plus lambda 3 summation over I Ei delta Ni should be how much? Should be 0. Now second thing what do we do is dividing both sides with what? Lambda 1. So if you divide here with lambda 1, how much you'll get? Log of Ni delta of Ni. On the second quantity, how much you'll get? Delta 2 by delta 1 summation over delta Ni. And on the third quantity, how much you'll get? Delta 3 by delta 1 summation over I Ei delta Ni should be 0. Let lambda 2 by lambda 1 equal to lambda certain quantity. This also a constant. Lambda 3 by lambda 1 also be some constant, which is beta. Now if you substitute this over here, what you'll get? Log of Ni delta of Ni plus lambda summation over delta Ni. I is also over here plus beta summation over I Ei delta Ni. Because this is summation over all i's, what we can do, we can take this as common and we can just put it over here. Over here, how much we have? Ni delta Ni. Lambda is constant, so it can be placed inside your summation. It's not a problem. Delta of Ni. And finally, you have beta Ei. Beta is also constant. Ei delta of Ni should be 0. Yeah. Or also you can take delta Ni is common from all this. Log of Ni plus lambda plus beta Ei into delta Ni should be 0. So from here, what we can see is your delta Ni is not 0, but only quantity which could be 0 is basically which is sitting inside. So that's why what we can write is log of Ni plus lambda plus beta Ei equal to 0. So from here you can find log of Ni can be written as negative of lambda minus negative beta of Ei, or Ni can be written as e to the power negative lambda minus beta Ei Or finally, what we can write, Ni is equals to e to the power negative lambda e to the power negative beta ei. Or Ni can be written as, this is some constant A, we write it beta ei. So this is what your number of particles. So give the number of molecules in each cell as a function of what energy associated with each particle in the cell. This is basically a Boltzmann canonical distribution law. This tells you how the particles are distributed among each and every cells at a particular energy, or basically how the particles are distributed between different energies. Is it clear?
Yes, sir.
So that's why, if you all remember, for the canonical we have written a weightage of this. Do you all remember? Weightage of e to the power negative beta ei. Yesterday in my notes, I think you can check my notes.
Yes, sir. E to the power minus beta e.
This is basically this. Now you can see how the particles are being distributed. This gives you the number of particles. Let's say N1 particles in energy E1. This is how they are being distributed. Clear? Let's say you have a cell of energy E1. Clear? And you have particle N1. So the N1 particle is distributed in this manner. Actually, there will be N1, N2, N3, N4, N5 such particle, but this is how they are being distributed. So basically, this equation gives the number of molecules in each cell. Clear? Number of molecules in each cell as a function of what? Energy associated with each particle in that cell. So number of particles in each cell as a function of energy associated with each particle in that cell. Is it clear? Basically, this will give you the number of particles in a particular energy. Basically, this is how the particle has been distributed. Now, if you plot Ni versus Ei, what you will get? If you plot Ni versus Ei, then what you'll get? You'll get a exponentially decaying kind of thing. Yeah. Now, what does this mean? Basically, what does this mean? Basically, all the system, what they want to do, they want to minimize the energy. Yes or no? Yes or no? Basically, what does this graph means? Do you see at lower energy, because the energy will be lower in this side and will be higher in this side? Do you all see? Number of particles is more at the lower energy and less at the higher energy. Because this is usually how the system behaves. Because they always wants to be in what? They want to minimize their energy. So the more number of particles will try to sit at such configuration where the energy is extremely low. So from this graph, also from the graph itself, we can also see that is happening over here. Really, the number of particles are more on the cell with having less energy. Can you see?
Yes, sir.
Is this point clear or not? I can explain it one more time. Is it clear or not? Indira, is it clear? Ruben?
Yes, sir.
Okay. Is it clear?
Yes, sir.
Because basically what all the system will try to be in here, it's ground state. Because why waste energy, basically? Okay, so always it will try to be in the state where its energy is minimum. So similarly over here, number of particles is maximum where your energy is minimum. Clear? Over here. So that's why we can see physically also that this distribution is correct. So this is your distribution for a number of particles for a given energy to be occupied in a particular cell. Till now, do you have any doubt?
No, sir.
No, sir.
Now, if the cells
Yeah.
are of different size, then what you will have? Then what you will just put a weighted factor. N1 is equals to A gi e to the power negative beta ei. Do you all remember when the cell was of different size? The size of the cell was given by what? Z. Z1. Another cell was Z2, which was of this kind of size. Do you all remember? Basically, what it will do is, for a given Gi, if this size is larger, let's understand it physically. Okay. Let's consider a system. Over here, all the cells were of equal size. Okay. Now, next what we do is, we make some of the cell larger and some of the cell smaller. Let's say this has a size of Z1, this is Z2, so on and so forth. So, N1 will be directly proportional to the area of the cell or not? Will it be directly proportional to Zi? Because the cell is larger, so it can accommodate more number of particles. So directly what we can write as Ni as a just a factor of Zi e to the power negative b. Is it clear? Usually this, sometimes we can have a group of cells. One cell, let's say another cell has a group of 4, one has a group of this. So each of these things are called zones. Zone or the size of the cell increases or decreases. So this zone is given by what? The factor of Z. How big is the zone? This is called the zone of cells. Clear? And looking from the dimension itself, also what we can find, your beta is what? 1 by kT. Clear? Here I have just directly written this as beta. One can derive, it's not a problem. From thermodynamic quantity also we have derived it previously. So basically how much is your beta? Is kT. And apart from that, we have to find what? A. Constant. Let's evaluate the constant A. Constant A can be given by what? You know, summation of all Ni will be what? N. This is constant. Yes or no? Because the total number of particles is fixed. So summation of Ni will be given by what? You have just done it now. Is given by A. Leave it Z e to the power negative beta ei. Ni can be written as this. Is it clear? So A summation over all E negative beta ei should be equal to N, or basically A is given by what? This is exactly a normalizing condition. Do you all see? A is basically this much, and whatever is sitting at the bottom, which is basically a summation e to the power negative beta is written by Z, which is called a partition function. Partition function. Is it clear? So basically this is what your A looks like. So finally what we can write, A as N by Z. And finally what you have, Ni can be written as A we can write as Z by E, e to the power negative beta E I. This is your final solution, and you know beta can be written as 1 by kT. We can derive it, but still we have derived it previously also, and still we are just putting it in this fashion. Is it clear? So from here, do you see in T instead of E we have T? Now we have already know how the thermodynamic quantity has been measured. From entropy, you know how to find the entropy. And this is a number of distribution of particle. Till now, do you have any problem? Till now, do you have any problem?
No, sir.
Okay. We will do one more topic, one more small topic. I'm just introducing this topic, okay? This is something called a Gibbs paradox. It's very nice. It's a nice kind of paradox. I'm just discussing this, okay? Now you have two boxes. Clear? You have a box which has a compartment exactly at the center. Let's say the number of particles over here is N1, V1, and the pressure is P1. I think that much is enough. Let's call this as box A and box B. Number of particles over here is N1 and the volume is V1. This is N2, volume is V2. Now initially there will be some entropy over here, S1, and the entropy over here is S2. Now if you open this compartment between these two and allow the two particles to mix, what will happen? Will the entropy increase or decrease? Because the gases now starts mixing. Will the entropy increase or decrease? Is this point clear? You have a two system and you just open the compartment and you allow the two particles to mix with each other. Will the entropy increase or decrease? Will the randomness grow or will it decrease? Is the question clear? I'm asking to everyone. Yeah, who is saying that it will increase? Yeah, Ritika, it will increase. Because the randomness will increase, because the number of particles has grown and the two particles have started mixing with each other. So the entropy will increase. Clear? Is it clear or not? Because there are different particles and they are mixing with each other. Let's say you have a huge number of people entering this hall. Clear? And there are certain number of 10 number of people are sitting over here and 5 number of people are sitting over here. And if both are allowed to move inside this new hall, will the randomness increase or decrease? It will definitely increase. So that's why the entropy will increase. So when you open this, what the entropy will be, new entropy, let's call it S3, will be greater than the sum of the two entropies which you had previously, because the entropy will increase. So now if we have an identical particle, exactly same gas molecules, what will happen? The entropy will increase or decrease? the entropy will be, the change in entropy will be what? Will be 0, because they are exactly the same particle. And this particle don't know whether this is this particle or not. So the randomness will not increase. Clear? Because even if the particle was sitting over here and another particle which came over here, because that is also belongs or is exactly the same particle. So the entropy, change in entropy will be 0. Is this point clear or not? Is this point clear? Why the entropy will not increase for an identical particle? Okay, because the both are identical, both are same, and they don't have information about whether this is different particle or not. So the entropy will be exactly same. So the change in entropy will be 0. Okay. Now what it was found is mathematically you will get some solution for the entropy for mixing of gases. Clear? And when you put a formula over there and when you evaluate the entropy before and after for the identical particles, then what you will get for the identical particles, you will see that the entropy is increasing. Clear? That we'll discuss it in the next lecture. Don't worry. What it was found was doing theoretically, and you got some formula for your entropy. And when you find the change in entropy, it was coming to be positive. Clear? But according to our physical intuition, the entropy should not change. But from the formula, we are getting some positive entropy. So which one is correct? Obviously, the one which has a physical interpretation, which is there, because the entropy will not increase. That is correct. But according to formula, we are getting the entropy to be positive. So there is some differences. So that's why it's called a Gibbs paradox. Clear? For other gases, it was giving the correct answer, but for only for the identical, it was giving a different answer. So that's why what? It's called a Gibbs paradox. So, okay, fine. We'll continue in our next lecture. I'll just take the attendance now.